So we're going to look at the ionic structure, how these compounds are put together, and then what properties this leads us to. So if you look at the picture, you have the positive and negative, and they're alternating, and that is called the lattice structure. So an ionic lattice, just that 3D structure, you have oppositely charged ions surrounding each other. So in this first picture, it looks like one slice of the compound, and so our positive charged atom right here, or our cation, is surrounded by 4 negative anions. However, you have to remember that it's a 3D structure, so you would have a layer on top and bottom of this. So in fact, it's surrounded by more than just 4 ions. It would be surrounded by 6 ions, because you would have one on top and one on bottom. And that's only if it's a 1-to-1 ratio. The coordination number is the number of the ions that are around it. So for in this example, the coordination number would be 6, because you would have 6 anions surrounding the one cation. Now, we don't usually write our ionic compounds like this. Instead, we give the formula unit, which is the simplest ratio, which is also called the empirical formula. But we refer to it as the formula unit when we're talking about ionic compounds. Now, when we move into Chapter 5, or Unit 5, or Topic 5, we'll actually calculate the lattice energies, so what that actual value is between the positive and negative, and the strength and the energy it takes to break that bond. So ionic properties, the first one you have to know is that they have high melting points and high boiling points. It's not necessarily higher than metallic. We just labeled both metallic and ionic high melting and boiling. But it's the energy needed to overcome that electrostatic force. Now, the larger the ionic charges, so if you think about +2 and -2s as opposed to the 1 in sodium chloride, the stronger that lattice energy is, and so the higher the boiling point goes. So the larger the charges are, the more energy is needed to melt or boil. If you look at the size of the atom, the smaller the atom is, or ion is, the more energy is required. So make sure you have written down in your notes that the larger the charge and the smaller the ionic radius, the stronger the atom, or the stronger the bond, and therefore more energy is needed to melt and boil. Larger charge, smaller ionic radius, stronger ionic bond. Solubility, we should remember from Chem 1, is the ability to dissolve in water. Remember, water is polar, so it has that positive end and negative end, and so it can pull apart our ions, and that pulling apart is called solvation when it's surrounded by water molecules. And so if you look at the negative anion, it's surrounded by the positive sides of water. The positive cation is surrounded by the negative end of water. Not all ionic compounds are soluble, and that's why we have to know our solubility rules. But in general, ionic compounds are soluble. The third property is electrical conductivity. Now, ionic compounds will only conduct if they are melted or dissolved. So when they're molten, meaning they're a liquid, or dissolved, meaning they're floating around as ions surrounded by water molecules. And the reason is because when ionic compounds conduct, it's the movement of the ions that allows the electricity or the heat to move through the compound, as opposed to metallic bonds where it's the valence electrons that are allowing that. So ionic compounds, it's the ions that allow and move to allow the conductivity to occur. Ionic compounds are also brittle. So if you look at the picture, I really like this picture because I think it helps explain it. You have an external force like a hammer. It pushes down on those atoms so that like ions are together, and since you can't have two positively charged or two negatively charged ions side by side, that's where it will break and crack the lattice or break apart the lattice. So it's brittle because we can force those ions with an external force to line up the same charges, and then they repel each other, which makes it break apart. Metals, if you're thinking about the types of elements, have the lowest ionization and electron affinity, so they always lose electrons to form cations. Nonmetals are the opposite. They have the highest ionization and the highest electron affinity, so they always form the anions. The farther apart they are on the periodic table, the more ionic character they have. So the farther apart the atom or the elements are, the more likely that electron is going to be transferred as opposed to shared. Now we can tell whether or not it's going to be transferred by looking at the difference in electronegativity values. Remember, electronegativity value is how much the nucleus can attract electrons in a bond. So if the difference between electronegativity is greater than 1.7, it's ionic. If it's between 0.3 and 1.7, it's polar. And if it's less than 0.3, then it's nonpolar. Now these values are given to you in section 8 of your data booklet. So pull that out. And let's look at two examples: potassium and sulfur, beryllium and fluorine. So pause the lesson, calculate the difference, and see if you can figure out the type of bond. So potassium, based on our electronegativity values, is 0.8 and sulfur is 2.6. You always do big minus little, so that gives us a difference of 1.8, which makes it slightly ionic. Beryllium is 1.6 and fluorine is the most electronegative at 4. So when we subtract the difference, it's 2.4, and so that is ionic. So beryllium and fluorine is more ionic than potassium and sulfur because it has the greater difference.